Welcome to Green Chemistry, Frontier Molecular Orbital Control in Green Synthesis Design. We will build intuition for how highest occupied and lowest unoccupied molecular orbitals guide reactivity, and how that helps us design cleaner, less wasteful reactions. We will explore the chemistry, the math, the statistics, and the graphics step by step. First, the basics. Frontier molecular orbitals are the highest occupied molecular orbital, the HOMO, and the lowest unoccupied molecular orbital, the LUMO. Reactions often occur when a filled HOMO from a donor interacts with an empty LUMO on an acceptor. The vertical position represents energy. Blue lines show the donor, and red lines show the acceptor. The key quantity is the gap between the donor HOMO and the acceptor LUMO. A smaller gap makes interaction stronger and lowers activation barriers. The other key factor is overlap. If the phases match where the orbitals meet, the overlap integral grows. This overlap is written as S equals the integral of phi h times phi L over space. The interaction energy from second-order mixing scales like minus beta squared over delta E, where beta is proportional to S. Kinetically, lowering the activation energy speeds up the reaction rate. The rate is proportional to the exponential of minus EA over RT. Frontier orbital control reduces the barrier by increasing overlap and shrinking the gap. A simple example idea. A hydrogen-like donor transfers into a carbonyl system by targeting the carbon-centered LUMO. Aligning the blue donor HOMO with the red acceptor LUMO increases overlap and lowers the barrier. This principle guides greener routes by enabling milder conditions and fewer byproducts. Green synthesis aims to maximize atom economy and minimize waste. Atom economy is the fraction of reactant atoms ending up in the desired product. The E factor is kilograms of waste per kilogram of product. PMI is process mass intensity, the total input mass over product mass. Let's compare two hypothetical routes to the same target. Route A is FMO guided, and Route B is a traditional approach. We can also sanity check with data. If we screen catalysts or solvents that tune frontier levels, we often observe that a smaller gap correlates with higher yield. This scatter shows that trend. As delta E decreases, yield rises. In practice, green levers include selecting catalysts that stabilize the LUMO or raise the HOMO appropriately, using light to access excited states instead of heat, and aligning orbitals through stereoelectronic control. These molecular level choices reduce temperatures, solvents, and waste. To summarize, chemically, reactions follow frontier orbital interactions, dominated by the donor HOMO and acceptor LUMO. Mathematically, interaction scales inversely with the gap and directly with overlap. Kinetically, smaller barriers mean faster rates. Statistically and graphically, we use metrics and data to pick greener routes. Frontier molecular orbital control gives a powerful lens to design greener syntheses. Fewer steps, milder conditions, higher selectivity, and less waste. Thanks for watching.